சார் லைவ் ஸ்டார்ட் பண்ணிட்டேன். நீங்க ஸ்டார்ட் பண்ணலாம்.
Yeah.
Questions இல்லனா நம்ம க்ளோஸ் பண்ணிடலாம் சார் செஷன். ஒண்ணும் ப்ராப்ளம் இல்ல.
Yeah. Hello students. Welcome to the live session of welding processes course. I'll be happy to interact with you if some of you are around. Sorry about the delay. There was a little communication error between like myself to be blamed for that. I thought it's 6 o'clock. Anyway, I'm sorry about that for a 10 minutes delay. So if you have any questions to be to be asked and to be clarified, I'll be glad to answer, and we'll take up the questions one by one if you have, and you can either add it in the chat window, or you can also put it in the YouTube chat, or some of you must have already sent some questions. I will have a look at when we go along, and so let's try to answer some of the questions. I'll also try to get some questions from the forum, and if any of you still want to discuss about the questions what you have already placed in the forum, we can also discuss again. Yeah, good. Thank you guys for attending this course. I hope this course is actually useful for developing your knowledge on welding processes. And some of you are working in various manufacturing industries. I just see from your profile. So I hope you can enhance some of the knowledge what you want to develop. Yeah. Good. So let's see if any other questions are there. We'll try to get. Karthi, is it live? I see YouTube is still saying waiting for the interaction session.
Yes sir, we are live sir, YouTube. Yeah.
Okay. Yeah. So let me check whether it's a correct link. Yeah, I think so. Okay. Yeah. So Prakash, you can also read the questions if there are any questions in the Google response sheet. So what we can also do is quickly go to the discussion forum in the course page, and I'll try to answer a couple of questions in the discussion forum. Meanwhile, now if you have any questions, you can also post it in the chat. Yeah, so I'm just grabbing the questions. So I see one interesting question in the chat forum on the polarity concept, right? So I think Mr. Satish asked this question. Yeah, so the question is, so he likes to understand the basic concept about why in non-consumable electrode welding, like in a GTAW, DCEN polarity, the electronegative polarity, the penetration would be higher. And in GMAW, in the consumable welding process, DCEP polarity penetration is higher. Okay, so we'll have to go back to the discussions what we had in the first, I think maybe in the second week lectures, in my opinion. I'll just grab this slide, and then we can try to explain this concept, how the polarity, change in polarity would influence the depth of penetration. Okay, so if you can recall the lecture slides, what I showed you, maybe I'll try to share the content. I'll just grab first the slides. Yeah, so let me share my screen. I hope you can see it. Yeah, is my screen visible?
Yes, sir. Yes, sir. Yeah.
Okay. So probably this is the slide what you're referring. I'll just open it in Acrobat, so it will be easy for me to annotate. Yeah, sorry about this. Okay. So when I taught this slide, so I was referring about the changes in the transport of fundamental charge carriers, right? So when we use a straight polarity, which is electronegative polarity, the electrons are traveling from the non-consumable electrode. Okay, this is in a gas tungsten arc electrode, right? So if the non-consumable electrode is used, the electrons are made to transport from the electrode towards the base material. So what happens? So in the subsequent lectures also we see when the electrons are traveling, the electrons carry more heat, right? So they tend to create more heat, and then that heat is actually transported to the work plate. And when we have the electrons are moving from the electrode tip to the base material, obviously more heat is transported. Okay, and therefore the penetration increases significantly. Right? In consumable welding process, if you switch the polarity, okay, so for example, in a consumable welding process, so if you have a reverse polarity, DC RP or DC electrode positive, where we make, so this is a positive and this is negative terminal. So now what happens? We change the directions of electron transport, isn't it? The electrons would tend to travel from the base material towards the consumable, right? So now what happens when we have the electrons are traveling from the base material to the consumable? So obviously the more heat is actually concentrating on the electrode. So therefore we melt more of electrode, right? So if you melt more of the electrode, so obviously we have more volume of molten metal transported to the base material, right? So the heat is not lost. What happens in the conventional welding process when you use a direct current electrode positive? If you recall back the efficiency calculations, what we actually do in the consumable welding process, so the both, right, the efficiency calculation when we look at, so we add up the heat which is available, so in the electrode as well as the base material. So the heat is actually generated or accumulated at the electrode. The heat is again sent back to the base material. So heat is not lost. The efficiency is higher because whatever heat is actually used in the electrode is again going back to the base material. So that means that, so we also melt more. Okay, the consumable is molten and the heat is actually given back to the base material. Okay, so obviously because of the addition, the two term, see both the heat which is actually used by the consumable to melt is actually going back more or less the same amount. So therefore, when we change the polarity, okay, so we melt more of the consumable, right? And that heat is transported back again. So obviously the penetration will increase in the consumable welding process. Okay, so in both in a DC EP polarity. Yes, I hope this is actually clear. So I'll also take you to the efficiency calculations, what we have done for the consumable welding process. Okay, so we'll just move some slides. Yeah, we'll have to go somewhat long back. Sorry about this. Almost there. Yeah. So you see this. So if you look at in the consumable welding process, the energy present in the cathode and anode are added up together, isn't it? So if you make our consumable electrode, okay, as the anode, which in the case of DC EP case, again, whatever heat is actually absorbed by the consumable, it is again going back to the base material, isn't it? So that's the reason. So we have higher penetration, okay, even DC EP case. So I hope this is clear for Mr. Satish and others who are actually asking about the polarity concept, right? Good. Are there any other questions in the forum or in the YouTube live? Yeah. Good evening. Yeah, Prakash and Ramki, are there any other questions?
No questions, sir. No one asked.
Okay, so maybe we'll try to discuss. I think I found another interesting question. Okay. In the flux core arc welding, the melting rate. Okay, there was another question. Okay, so it says that the melting rate, again, the DCN is higher than DC. How is it possible? Okay, but the melting rate is also a function of stick out length. That's what I think my TAs have already answered the questions. So you need to really look at the actual melting rate equation to calculate the melting rate as a function of stick out length, the current, so what we use, also the electrode radius. Good. So there are other simple questions which already been answered extensively by my TAs. Okay. And there is another question about the difference between the vapor pressure and recoil pressure. Okay, so vapor pressure and recoil pressures are different. Okay, recoil pressure is generated by the escape of vapor from the keyhole. Okay, so the opposite force created by the escaping vapors. Okay, from the keyhole towards the atmosphere outside. Okay, good.
This
Yeah.
is Prakash.
Yeah, Prakash.
Sorry, in the discussion forum, actually, we already answered some 3 questions, but I found a little bit interesting in some questions, sir. So can I?
You can read.
Can
yes.
you discuss?
Yeah.
Yes.
Yeah.
So in the chapter 1, slide number 9, in that voltage versus current graph, like we can see the Townsend and glow discharge and arc discharge. In that graph,
yes,
one student have asked that why the voltage has increased suddenly after the glow discharge in a very short range of current.
Okay, so the graph what I showed you, which question you're referring in the forum?
In our January 17
email
at 11 p.m. sir. Harik, I think, sir, his name.
Okay, so January 17th, isn't it?
Yes, sir.
Graph shown in voltage, why the voltage has increased suddenly after glow discharge. Okay, so the graph I showed you on the description of various discharges. So the current voltage behavior is unique to the various gases what we use. Okay. So the after glow discharge, okay, so if I can understand the questions properly, why the voltage has increased suddenly after glow discharge in very short range of current, okay? See, the discharges are all determined by various physical phenomena, what we actually realize in nature. Okay, so for example, glow discharge is characterized by the ionization, but the number fraction of the ions we create in the glow discharge is much lower than what we do in arc discharge. Okay, because in arc discharge as such generate more heat because of number of ionization incidents. We have increased the amperage significantly higher. Okay, so what happens when we increase the amperage higher, the number density of electrons are also increased significantly. So more number of electrons, that means that more number of ionization events, right? In glow discharge event, the number of ionization events are very small, okay, right? And if the voltage between the positive and negative terminals, okay, if that is actually increased to beyond the threshold level of gold discharge, okay, we tend to ionize, okay, so more neutral atoms, right? So whatever ionized would tend to increase in acceleration because of increasing potential difference, right? And this, the graph what I showed you, it is particular for argon gas. Okay, so it is a behavior of argon gas, where in argon, when it undergoes a glow discharge, the moment the voltage increases beyond the glow discharge voltage, where it can be sustained, there is sudden increasing in the ionization event. Okay, so what happens? So when the voltage is increased, the number of ionization incident is also increasing. And argon, when we use argon, also has a very high ionization potential, isn't it, compared to metal vapors? To increase the ionization event, okay, whatever gases are ionized just below the threshold voltage, the number of ions that are actually produced, they'll have to be accelerated so fast, instantly, so that we can ionize more amount of gases, atoms, neutral atoms, right? So what happens when the glow discharge is actually ending by increasing the voltage? So at this point, okay, if you want to break this glow discharge, or if the voltage is increased even slightly higher, okay, than the threshold voltage, the number of ionization event, okay, would still be similar. Okay, the other means number density of electrons that are actually there in the system, okay, would still be similar, because of the fact that argon has very high ionization energy. So in order to further ionize the argon gas, okay, so we need to increase the voltage significantly, okay, so that the already the ions which are present in the system can be accelerated so in high velocity, in such that these accelerated the ions and the already present, the electrons which are present in the system, can be accelerated by increasing in the potential difference. And during this process, they can collide with the neutral atoms and promote subsequent ionization event. The avalanche, that's what we describe, right? So in the arc ignition process. And it is a combination of high ionization energy of argon and the critical threshold voltage to sustain the glow discharge. And these two combines, and when we increase the, say for example, voltage, we need to increase the voltage significantly higher to get more number of electrons that are generated by the ionization event. Okay, so that's the reason. I'm sorry about this. So that is the reason. So there is an increase, sudden increasing in the voltage to further, okay, promote the conductivity inside the gas medium. Yes, is it okay, Prakash?
Yes, sir. Yes, sir. No.
Yeah.
But,
yeah. So good. So any other questions?
questions in the even YouTube also.
Yeah, so the YouTube video is still on. I mean, I'm not seeing any video in YouTube. The link what is shared with me. Yeah, Karthik, can you send the YouTube link again? Because I don't see any chat. Anyone? People are saying good evening. That's it.
Okay, I will send you. Yeah.
Yeah.
Sorry, இப்போ chatல போட்டுருக்கேன்.
Yeah, so I'm just seeing it. So I'll just yeah. Okay, so I see so another question from Mr. Sarvesh Tripathi asked on a question. Lattice girders of the tunnel were not cleaned and welded the bar. Mr. Tripathi, can you explain the question slightly better, if possible? So the welding is not carried out without proper cleaning, right? So we may have a problem, right? So when the girders are not cleaned properly, okay, when it is welded, so there is a possibility of like oxide entrapment, and so that there is also possible problem with the alignment. Okay, so without looking at the structure, it's very difficult to comment on that. Yeah, I think most of the other questions are all related to assignments, so they're all answered. Okay, so then if there are no more questions, probably we can wind up. Yeah, Karthi.
Sir, நம்ம end பண்ணிக்கலாம் sir, session end பண்ணிக்கலாம்.
Yeah, so we can.
Okay, yeah. Thank you, sir. Yeah.
Thanks. Yeah.